Yeah, DC circuit analysis, chapter 4. Yeah, series circuits. Before we start talking about series circuits, we want to talk about some basic elements. Okay? We're going to talk about the ideal basic elements and some of the attributes of that. It says that the ideal basic element has only two terminals. Okay, and I have it drawn on the screen for you. It's described mathematically in terms of circuit variables of current and or voltage, and the ideal basic element cannot be subdivided into any more elements. You can see here that I have a box drawn, and notice that the box is blank because at this point there's been no commitment on what actually the box is or what it does. But we do have a reference voltage assigned to it and a reference current in the indicated direction. Now the mathematical formula inside could be anything. We haven't defined that yet. But what we have defined is a voltage, V, a reference voltage, that is with a plus on terminal 1, a minus on terminal 2, and a voltage in between the two terminals. We've also designated a reference current going into pin 2, which that current would also have to flow out of pin 2. So if it's flowing in pin 1, it would therefore have to flow out of pin 2. Because the current doesn't go into an abyss somewhere and never return. It's kind of like, eventually the current's going to have to come out. Maybe not exactly at the same time, but there is going to be the current coming out of the terminal. Note that we've only defined at this point, we have a V in the middle. Okay, this is called the reference voltage. Now, if V happens to be positive, then what we're defining here is that there is a rise in voltage from terminal 2 to terminal 1. Okay, if V is positive. Does everyone see that? Because notice the direction of the sign. We have a plus and a minus. By that direction, by that plus and minus, we are indicating that terminal 2 is at a lower voltage than 1. So therefore, that would seem to indicate that if you went from going from the second terminal to the first terminal, you would have a rise in voltage. That's the same thing as saying if I went from terminal 1 to 2, I would experience a drop in voltage. Okay? Now, what if I say V is negative? What if I say, well, V was 1 volt, but now I'm going to say V is minus 1 volt? Well, then that would seem to indicate the exact opposite. If V is minus, then what? If we come in here and say, well, V is minus, then this is not going to be a rise anymore, is it? Now it's going to be a drop. So if V is negative, there is a drop in voltage from 2 to 1. There's going to be a drop.
That doesn't make sense to me.
Well, it has to make sense. Because if V is positive and there's a rise, if you say V is negative, then it has to be a drop.
Yeah, but you've already indicated that 1 is
It's a reference.
voltage and 2 is the negative.
No, we're talking about reference. We're not saying that it's actually that voltage. We're defining a reference voltage. That's the entire point I'm trying to get across. Is that when you assign variables, we're assigning variables. We're assigning a reference voltage. The reason we're assigning a reference voltage is now we can write V And we can say V is 1, or we can say V is 2, or we can say V is equal to minus 2. We're not going to change our reference direction.
Okay, so you're not indicating polarity there.
It's a reference. You have to have a reference. I'm not actually telling you, this diagram is not actually telling you which direction the current's flowing, and it's not telling you.
It does indicate where the current.
No, it's a reference. It's a reference.
So then the whole thing's a moot point.
Reference. No, reference. It's not a moot point. It's a reference.
What are we referring to?
For real. We're having an issue here.
Okay.
We're not getting it.
Okay. If I define this current and say that's a reference current, that means it's not actually flowing. It's a reference. It's kind of like saying, if you have a one-way sign that says this is a one-way street, does that mean you have to go that way? No, it says you should go that way, or that I'm going to define that. Right? This is not saying that what's actually happening. It's a reference for you to say, okay, if the current is flowing 1 amp this way, then we're going to define that as being positive current because it's going in the direction of the arrow. If we actually determine that our current is flowing this way, we're going to say that the current is negative. It's a reference.
So what we have to know is that if our conditions are correct according to the reference, then that's positive.
Yeah. We're defining a reference.
The reference is negative.
Let's say that we get rid of this reference and we completely diminish an entire concept of reference.
Okay.
And I say, there's 1 amp flowing through this element. There's 1 amp. Or let's say there's 2 volts across those terminals.
So you're measuring from pin 1 to pin 2.
No, I didn't tell you that. See, there's no reference. Now, the first thing you're going to ask me is, okay, so where's that from? Is that voltage from 1 to 2? Or, well, this is telling you what that is. This is telling you what I mean when I say there's a voltage across. If I say there's a voltage across pins 1 and 2, and that voltage is 1 volt. And you say, oh, okay. So that means that you have a higher voltage on pin 1 than you do 2. And I say, yes, that's right. You're measuring from pin 1 to 2, pin 1 being positive, pin 2 being negative. Because if I don't have the reference, and I say, go measure that widget over there should be 1 volt across it. And you go over there and measure it, go, yeah, I got 1 volts. What side's positive, what's negative? Does it matter?
Yeah.
It matters.
Depends on which device.
So the fact that it matters is why we have the reference.
Okay.
So now, if I say there's 2 amps flowing this direction, what is I equal to? Negative 2 amps. Yeah. See, that's how it works. Let's say I have 5 amps flowing this direction. What's I equal to? Huh? 5 amps.
Oh, yeah, 5 amps.
That's the way it works. We define a reference direction, and we don't really care which way that we just want to have a reference. We want to have something so we know how to communicate between different people, the engineers or whatever. Now, let's say that I have 5 volts. Let's say that I take a voltmeter and I put 5 volts across those 2 terminals. What is V equal to? 5 volts. What if I come over here and I connect a 12 volt battery like this? What's V equal to? Negative 12 volts. See? That's the way it works. The reference always stays the same, and you can flip the battery around however you want. You can change the voltage to 12. Maybe it's going to be 9 to 12. Maybe it's going to vary. So that's what we're doing at this point. So if the value of I is positive, the current flows from terminal 1 to 2. If the value of I is negative, then positive current is going to flow from terminal 2 to 1. So if I is positive, if I is plus, then current is going to flow this direction. Okay? If I is negative, current will flow this direction. Does everyone understand that? The assignments of the reference polarity The assignments of the reference polarity for voltage and current are entirely arbitrary. They set a baseline point for someone to have conversations to. Okay? And if you don't have a reference point, then the first thing someone's going to ask you is, well, what are you talking about? What from what to what? Which direction? So we have to have the direction. However, once you assign the references, you must write all subsequent equations to agree with the chosen references. And the most widely used sign convention, we call this a sign convention, is called the passive sign convention. What is the passive sign convention? Passive sign convention is the convention we're going to use in this book when assigning currents and voltages to passive devices or active devices. Passive devices are like resistors. Really what it's trying to refer to is the fact that a passive sign convention will be a passive component normally consumes energy. It doesn't deliver energy. So for a passive component, the current is always going to flow in the direction of the voltage drop. Passive sign convention always flows in the direction of the voltage drop. And the key word is passive, so a passive component dissipates or uses energy. It does not deliver. What does that mean? Well, what does that mean? What that means is, say if we have an element here, and we have a terminal 1 and 2, and if we say that we have a voltage, this will be the passive sign convention. Why is that passive? Because the current, we're indicating that the current is going to flow in the direction of the voltage drop. Now what that indicates to us is that the element itself is not generating electricity, but it's actually consuming electricity. It's consuming energy. So that's why we call it passive. If you were to assign I in this direction, for example, this would not be considered a passive sign convention. This would be because this component is really generating electricity. It's like a battery or a generator. Why? Because the current is flowing in the direction of the voltage rise. That means it's an EMF in this case. We define EMF. EMF is that which tends to push electrons, not consume them. So in this case, this is actually an EMF. Notice that the current is coming out of the positive terminal instead of going into the positive terminal. Yeah. Yeah, pin 1 is going to be sourcing current, but it's not really. That's not really the key. The key is that the current is going in the direction of the voltage rise. Because you could have. I could draw this arrow this way. I could draw this arrow this way. It's still coming out. It looks like the current's being sourced, but it's in the wrong direction. This is still passive sign convention. This is passive still. Because see, you're coming out of terminal 2 into terminal 1. See, it's really the same thing. Because the current's flowing in and then coming back out. So, as a review, Corey, how would I indicate passive sign convention on this circuit?
Current's flowing from 1 to 2.
Current's flowing from 1 to 2. Right. I would denote that as being I. So once you have assigned it, you must use it for all subsequent equations. Reference direction for current is in the direction of the voltage drop. That's correct. Ideal basic elements. Ideal means, what do we mean by the word ideal?
Well, we like that. The perfect form.
Ideal means that the basic circuit element does not actually exist. It's not really a realizable physical component. That's sometimes the hardest thing for people to understand. What we're going to get into now is we're going to get into mathematically modeling everything. The inductor, the capacitor, the resistor. Remember when we started talking about inductors? And we said that an inductor also has what? It's more than just inductance, it's also what? Inside of it.
Electromagnetic field, EMF, counter EMF.
Well, it also has a resistance.
Oh, yeah.
Remember we measured the resistance?
Right.
You cannot separate the resistance out of the inductor. It's part of the inductor. So if I draw a inductor symbol and I say this is an ideal inductor, that's not physically realizable. You can't have an inductor that's perfectly an inductor and not. In other words, what I mean is a physically realizable inductor is going to have a series resistance in series with it. So this is a circuit diagram of a physically realizable inductor. And not only that, a physically realizable inductor would have also parallel capacitance. We would say that R, L, and C in this case, these elements that make up this practical inductor, are made up of ideal basic elements. Ideal basic elements. So the ideal basic element does not exist as a realizable physical component. But ideal elements can be connected to model actual devices and systems. And the example is the one I gave you at the top of the page here. This is a model for an inductor. But many times on a schematic, you'll see this will be the model. That'll be the inductor. But you have to realize that if you push down inside of that inductor into the actual computer program, it's going to have this R, L, and C inside of it. So really, this is just the symbol. It's not really showing you the, quote, model. Okay. Ideal means that we can formulate a precise mathematical relationship between the terminal voltage and current. It means we can write an equation, we can put it in a program, and we can make the program spit out the right answer. Basic means that the circuit elements cannot be further reduced or subdivided into other elements. It's the lowest level that you can get. You can't get any lower than an ideal basic element. Okay? That's the number one thing I want you guys to learn from this slide. You cannot go any lower or any simpler than the ideal basic element. Basic elements.
Excuse me, so does that mean we would only have one resistor, one capacitor?
We're going to go through what are the basic elements. Like we'll have an ideal inductor, an ideal capacitor, an ideal resistor. When we use the word ideal, what we mean is it's not a resistor over there in the bin. It's a perfect resistor.
I understand. I mean, in the when you talk about basic, if you do a basic circuit, you just show one resistor for all the resistors in the circuit.
Well,
One,
this is what I mean by basic. If I drew a schematic with an inductor in it, and this was an inductor that you could actually purchase and put in a design, this is not, neither is it ideal, neither is it basic. It's not basic because this symbol is made up of elements below it that are more simple in design. In other words, this inductor that you have here is going to have a series resistance and a series inductance. It's going to have a parallel capacitance around it. So from that standpoint, it cannot be reduced any. This can be reduced to a simpler form using basic elements. But the basic elements themselves cannot be reduced any further down to any other form. It's kind of like saying the atom is the most basic building block of matter. For now, until they decide that something else is more basic. It's really just a definition. You know, they may come up and say, well, actually atoms are made up of smirk atoms or something. Okay. And those little smirk atoms actually make atoms. Okay, but until they say that, we're just going to decide that atoms are the most basic building block of matter. And it's the same way here. We're going to say that whatever we define to be an ideal basic element is going to be the lowest level that you can achieve. So, basic elements form the building blocks for constructing models. Now that's the key word too, models. We're not trying to construct, for example, we can take an inductor from a bin over there and we can say, okay, this is an inductor, but what's inside? What's inside of this? I mean, how can we model this? What that means is, how can we create a mathematical model, put it in a computer program, and simulate what it's actually going to do back there on the bench when you connect it? You know, so we want to be able to predict how the element is going to work on paper or on a computer program. So that's what we mean by modeling it. Because really, it takes a lot of time to build the circuits that we build. You can see that there's a lot of problems with wiring. It's a lot quicker sometimes to do on paper very simple things. Really quickly you can determine the solution on paper, or you can put it in a computer program. You can build these models using basic elements, and you can come up with a very complex solution and really understand what's going on inside of it, measure the currents and things like that a lot quicker than you could back there on the bench. It would take a lot longer.
so for each real component, you're going to have several basic elements.
Yeah, so the basic elements form the building blocks for constructing circuit models, but they themselves cannot be modeled with any other type of element. So, for example, if I say that this is an ideal basic capacitor, well, I'm not going to be able to model that ideal basic capacitor with any other component. If I have an ideal basic inductor, for example, I cannot model that capacitor with an inductor. And if I say this is an ideal resistor, an ideal basic resistor, which we're going to probably shorten the term to just ideal, an ideal resistor, this resistor cannot model that capacitor. They're completely different. So this is an R, this is an L, this is a C. Those are the three most basic ideal passive elements that we're going to spend the focus of this class on. Really, even just resistors, really, we're going to spend a lot of time just doing ideal resistors. But when you go to AC circuit analysis, we're going to spend more time with C and L. And you will be amazed about how complicated having these three components put in series and parallel and convoluted fashion you can imagine. You'll be amazed how complicated not only the math can be, but the analysis, the computer simulation, and everything. You can do a lot. You can do a lot with these three components. And then if you add semiconductors, yeah, it gets really complicated. So, we talked just briefly about the three basic ideal components: capacitor, resistor, inductor. But those three elements absorb energy. Hence, we use the passive sign convention on them. Now, in order to do anything useful, we have to have a source for the energy, a source of voltage or a source of current. When we say the word source, okay, that means a device that is capable of converting non-electric energy to electric energy, and vice versa. Vice versa, because many times the sources that are able to deliver energy, they're also able to consume energy as well. For example, a battery, right? Your cell phone battery is, right now as we speak, unless you have it plugged in, it's delivering current or providing current. It's converting chemical energy into electric energy for you right now. However, if you take your power adapter and plug it into your phone and plug it into the wall, a generator is going to be spinning in some magnetic field somewhere in some turbine, and it's going to be producing a voltage via Faraday's law. It's electromagnetic induction. It's going to be sending that voltage down a wire. Okay, so that's actually converting mechanical energy into electrical energy. The electrical energy is passing down the line. Transformers are stepping it up and down, eventually down, 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 and going to be converted down through your power adapter. Is going to convert that from AC to DC, and then that DC voltage is going to go into your phone, 5 volts, micro USB or USB, mini USB, probably micro USB, and charging your battery. And it's going to take that. What it's doing is taking that electrical energy, and it's converting that chemical energy inside of the battery. It's re-separating out those ions and allowing it to store more charge. So a source means a device is capable of converting non-electric energy to electric energy. A discharging battery, we already talked about it, a battery being charged. And a dynamo is the original word for a generator, can convert mechanical energy into electrical energy. It's just what we would call a generator. The original term was dynamo. Also, for example, a solar cell. A solar cell can convert light energy or photons into electric energy. Practical sources generally maintain either voltage or current. Okay, so we're continuing to talk about current and voltage sources. And for example, like an LED cell is typically going to have, if you put it in the sunlight, it's going to generate a current. And the voltage that it has across it, it's going to be fixed. But the more the light that you shine on the LED, the more current that's going to allow to flow through that. For example, a battery. Okay, a battery, its voltage is going to change as it's being charged or discharged, but its voltage is going to be fairly constant, not exactly constant, not perfect. So you don't really have any perfect voltage or current sources except when you get to like a power supply. Power supply is designed to deliver a constant voltage, a regulated voltage that's close to ideal. Close to ideal. But for example, let's look at maybe a battery. A battery discharges in a fashion similar to this. If this is V and this is time. So you may have maybe a lead acid battery, 2.1 volts, and then it maybe could charge down to 1.8 or something like that. At a certain point, it's just going to start to really drop off really quick. And then you're going to turn on your, hopefully before it gets to this point, you're going to turn on your vehicle engine and it's going to charge it back up. And then when you stop your engine, then it's going to start to discharge it back down. But usually, every time your vehicle's on, it's charging the battery, so you always maintain that top to level of charge. So, what does that mean? That means that is your battery an ideal voltage source? Can we model the battery with ideal components?
You could model it.
Yeah, we'd have to model it. We'd have to add some things to the... If we had an ideal voltage, let's say that I said that this is... If this is an ideal voltage source... I'm kind of getting ahead of myself a little bit, but... If I say this is an ideal voltage source, that does not really model a battery, right? If I was going to model this battery, I would have to have a voltage source and at least a resistor, even just to begin to model that battery. Because the battery is going to have internal resistance. Why? Why does the battery have internal resistance?
Because the bubbles on the different units, the resistance in the dielectric material inside.
Electrolyte. Most of it comes from the electrolyte, the chemical, the liquid inside the battery, because the liquid, they're conductive, but they're not as conductive as a metal. Yeah. So practical sources generally maintain either voltage or current. For example, that power supply back there, you usually set it on a particular voltage. Now they do make current sources that will just maintain a constant current, and you can use a transistor to maintain a constant current. So usually for voltage sources, we would say something like a DC generator or a battery would be a practical voltage source. The challenge, though, is to model practical sources in terms of the ideal basic elements. So we have to, in order to model a battery, we would have to add, like I said, a resistor at least and an ideal voltage source. Ideal voltage and current sources can be divided into two broad categories. Those are independent sources and dependent sources. Okay, so we got two major categories of sources. And then we have voltage and current, so that gives us actually four. Because we have voltage and current sources, and then for those sources, each one of those has either independent or dependent. So that really gives you four ideal basic sources. Independent means, wow, that's amazing. The independent means it's independent of any other voltage or current that exists in the circuit to which the source is connected. Okay? So an independent voltage source is independent of any other voltage or current that exists in the circuit. Does not depend on. Dependent means that it depends on a voltage or current somewhere else in the circuit. That's going to become clear, hopefully, in just a minute. Okay. So, an independent source. This is actually an ideal independent voltage source, and it is a circuit element that maintains a prescribed voltage. Prescribed is prescribed by the V source. You can put whatever number here you want. 2, 5. We're going to define the voltage across the source with a variable. And then we can assign the variable to whatever numeric value we want. So what it does is it maintains a prescribed voltage across its terminals regardless of the current in the device. So if I said that Vs is equal to 2 volts, okay, and then I said, okay, I'm going to have 1 amp flowing through this, then I would say the voltage across that voltage source is 2 volts. Okay? And then if I said, well, the current has increased to 2 amps, the voltage across that voltage source is still 2 volts. If I increase the current to 1 billion amps, it's still going to be 2 volts. It's an ideal basic voltage source. Does not matter if there's no current, minus current, plus 1 billion current, minus 1 billion current, zero current. It still has 2 volts across it.
Can I get one of those?
Just like that voltage source back there. If there's no current flowing through it, if you set it to 5, it's 5 volts. If you use it to supply 1 amp to your circuit, it's still going to have 5 volts across it. The limitation with that is it's if you go past 2, it can't, because it's not designed to support that current. It's going to fold back. But, you can buy current sources that can supply that sort of a current. What does that button do? Oh, that button does that. Oh, I was using the wrong button. Okay. An ideal independent source, we can also have a current. So an ideal independent current source is a circuit element that maintains a prescribed current across its terminals regardless of the voltage across it. This one may be a little bit harder for students to understand. If I come over here, if I say that IS is equal to 1 amp, okay, let's say that's equal to 1 amp. First off, well, we'll talk about that in a minute. Let's say I put a battery across it, a 12-volt car battery. We say IS is 1 amps. If I increase this voltage to 14 volts, now what is the current? What if I decrease the voltage to 2 volts? What if I get rid of the battery altogether and short those terminals together? What if I break this connection? Nope.
I was trying to go along. There's an open, there's no flow.
Now that is a difference with current. Now current can't flow without a complete loop.
Right.
So, yes.
Voltage will flow, or will be up to the point of the open.
They don't try to make a 1 amp flow, but you can't actually have current flow with no complete loop.
So theoretically, the internal resistance would have
ideally what happens is, let's say we have 1 amp. Oh.
Yeah.
In regards to resistive circuits, this is more practically how it works. If we say we have 1 amp here, and we have 1 ohms over here, we're going to have 1 volt across this.
Voltage drops, average.
Now, if we have 2 ohms, yeah, if we have 1 amp, if we have 2 ohms, then we're going to have 2 volts across it. If it goes to 3 ohms, it goes to 3. If we go to 5 ohms, it's going to go to 5 volts across it. And you can imagine that as you continue to increase the resistance, the voltage is going to continue to increase. 1,000 ohms would be 1,000 volts. 1 billion ohms would be 1 billion volts.
Is
Now,
there a source that reacts like that?
do what?
Is there a source that reacts like that?
A transistor is a current source. A transistor is a current source. Yeah. Yeah. Yeah, so we do have devices that operate like current sources. Ideal dependent sources. Okay, so now we're going to talk about dependent sources. An ideal dependent or controlled voltage source is a source in which either a voltage or a current at some location in the circuit determines the voltage across its terminals. So with a dependent voltage source, we're going to say we're going to use a diamond shape. And it has a plus and a minus. We can have a VS or whatever, some sort of a variable. Now with the dependent, the key is over here in the equation. And sometimes what you can do is, you notice here it says VS equals A times VX. What that means is it's going to depend on some other voltage in the circuit somewhere. It could be across a resistor. Could be across anything. In fact, we could just draw a little box and say, this voltage at some other part in the circuit, this VS is going to depend on that VX. So another way to do this is say, just take this AVX and say AVX. That's actually typically the way we do it. So this dependent voltage source is whatever its voltage is going to depend on this voltage across this element. So it's a different part of the circuit controlling the voltage across this voltage source. So that's a dependent voltage source. We could also have that voltage source could also depend on a current somewhere else. So we could say that this voltage here is dependent upon some sort of constant times IX. Could be dependent on some other current in some other part of the circuit. So we could have possibly a resistor over here, and we could define this as being IX. And we could say that the voltage across this element, this dependent voltage source, is going to be whatever this current is flowing through this resistor times A. And we'll get into dependent sources later. Right now, we really just want to introduce you to the concept that they exist, and we'll get into actually using them at a later date. Similarly, we have also independent current sources. They work in a similar fashion to the dependent voltage source, except for they provide current. But the current source is not. The current source is going to be dependent upon either a voltage at some other part of the circuit. For example, A times Vx would be an example. A would be a constant. Vx would be some sort of voltage across an element, a resistor, capacitor, inductor, whatever, some other place in the circuit. In this case, we would say that this is a voltage-dependent current source. We could also say that this current is dependent upon some other current in the circuit. A current across the current through a resistor, or current through capacitor, through an inductor at another place in the circuit. Let's just go over some really quick examples. This says that example 2.1, using the definitions for the ideal independent voltage and current sources, state which interconnections in figure 2.5 are permissible and which violate the constraints imposed by the ideal sources. So look at number A, or letter A, the first one. Is that permissible?
Yes.
Why?
Well, they're in parallel, so that's, you maintain 10 volts, you just increase your current.
Nowhere to go though.
What's that?
Nowhere to go. Just cancel that.
So we have a 10 volt ideal voltage source across in parallel with a 10 volt. Does that violate any of the rules? What's the rules for a voltage source?
Maintain current constant.
The voltage across the terminals is not dependent upon any other current through the circuit or any other voltage, or it does not depend on the current in the circuit. So that does not violate because we have two 10 volt supplies. They're parallel with each other. And you do not have, as far as I can see, nothing is violating the fact that it's trying to force a prescribed 10 volts across both elements, both nodes. Okay? So there's no violation there. What about B? The current sources. You have a 5 amp in series with a 5 amp. Now the way a current source works is it maintains its prescribed current regardless of the voltage across it. So does this violate that statement? No, it does not violate the statement. Let's look at C. We have a 10 volt ideal voltage source in shunt or in parallel across a 5 volt ideal source.
Yeah,
That's not going to work because both supplies are trying to force these two nodes to different voltages. Right? You can't have 10 volts across these terminals and 5 volts at the same time. Okay? So one way to make this work is you'd have to add a resistor in here, or you'd have to add some other element in between them. What about this circuit? This shows a complete path of current, and then it has a 2 amp and a 5 amp in series. Is that possible? That's not possible. Because the 5 amp, the way a current source is supposed to work is this current source is supposed to have 5 amps through it. How can you have 5 amps and 2 amps at the same time? They're in series with each other. If they were in parallel with each other, it'd be a different story.
How about something parallel?
What about E?
That's possible, isn't it?
yeah.
That is.
Does that violate any of the criteria that we talked about so far? No, it does not. So this is perfectly valid. Yeah. A voltage source will maintain its voltage regardless of the current. So this 5 amp source is forcing 5 amps to flow through it. That's okay. A current source will maintain 5 amps through it regardless of what voltage is across it. So it's completely happy being where it's at right now. Happy, happy, happy. Is that as far as I got? Is there no more slides? Oh, maybe that's the end. No, we got more. Good. Because I didn't think we were over. Using the definitions of the ideal independent and dependent sources, state which interconnections and figures are valid and which violate the constraints. Which ones do you look like that seem to be red flags? Just looking at them. Don't read the text. Don't worry about that. Which one of these seem to be red flags here?
D, definitely.
D is definitely a problem. D is invalid because the current in the independent source is not identical to the current in the dependent source.
What about
See, the current's flowing the wrong way.
3 volts? Yeah. A is 5 volts, 3 volts.
B, the current's flowing the wrong way.
Well, these are reference currents. And another thing is you don't really know, since this is a dependent voltage source, you don't really know what's positive and negative on that one. Because it's dependent.
A.
Yeah,
A is messed up because
5 volts, 3
it's
volts.
having both 5 volts across it, and then it says VS, it says that's VS is 3 times. It says this voltage is 3 times VS. Is that possible? That's what that says is this is 3 times VS. That would mean that this would have to be 15 volts. And this one is 5 volts. And you connect them across each other, that wouldn't work. Okay, so that wouldn't work. So let's go, now that we've talked about the independent dependent sources, let's talk about the most simple passive ideal element. Passive components, like I said before, they consume energy or power. We have resistors, capacitors, and inductors. They consume energy. Really, resistors consume energy. Ideal inductors and capacitors actually do not consume energy. They store energy. But they're considered one of the 3 passive elements. The most basic one, and the first one we're going to talk about and be doing all of our work in initially, is resistors. It's kind of amazing to think about it, but we're going to be spending a lot of time just working with resistors and sources. So current sources, voltage sources, and resistors. We're going to do a lot of work. We got 10 minutes. We got 8 minutes. So there's 2 possible reference choices for the current and voltage at the terminals of a resistor. Now remember before we talked about the ideal basic element, and we had a little box drawn. Remember? We had some terminals. Now ignore this line here. This line is just due to my scanner. Sometimes it puts a line through it, but that line's not supposed to be there. Look at resistor A. Is that the passive sign convention or not? Yes, it is. So if we determine that V is positive and I is positive, then we would say that resistor is consuming electricity. But the reason we use we use this reference terminal, this reference voltage and current is because when you do circuit analysis, you may not know what the actual voltage is, or the direction of the current at any particular time. If I drew a bunch of resistors on the screen here with current sources, you're not going to know what direction the voltage is and what, well, you may know, well, it depends on how many I draw. Like I could draw a bunch of voltage sources in here, and I could put some voltage sources over here, and I could put some current sources over here. So given that, you may not know what the voltage is across this resistor. You don't know if it's what direction it is. That's why we've defined this whole idea of reference direction. What we're going to do is we're going to come in and we're going to assign a reference direction. In other words, you can just guess. Say, well, I think the voltage is going to be across this direction. And assign a reference current. For resistors, we're always going to use the passive sign convention. You don't have to, but as a general rule, you can. It's not going to matter because regardless of what reference direction you use, you're still going to solve the circuit and determine what the actual magnitude of that current and voltage is.
You're just assigning something
So you can work the problem. Otherwise, you're not going to be able to start working the problem. Once you work the problem, then you're going to say, well, I is 1 amp, or sometimes you may solve it and it may say minus 1 amp. If it's minus 1 amp, well, that just means you put your arrow in the wrong direction when you did the reference. But it doesn't really matter. Because either way you do it, you're still going to know what direction the current's flowing. But it is kind of neat to try to assign the correct direction and see how many times you get it right and wrong. So that's usually what I try to do is say, I think it's flowing this way. And if it's minus, it's like, oh, okay, well, you guessed wrong. But it's not really a negative thing it's not considered a negative thing to get the current or voltage, backwards when you assign them. Okay. This is just going over Ohm's Law. If you use the passive sign convention, I guess I'll go over it. If I can get my pad. If you use the passive sign convention, which is that direction, then the equation for the Ohm's Law is going to be V equals IR. If you do not use the passive sign convention, then Ohm's Law is going to be V equals minus IR. So you need to be careful. That's why we use the passive sign convention. If you use the passive sign convention, you're declaring that element is dissipating energy or consuming energy. If you don't use the passive sign convention across the resistor, then you're saying that resistor is sourcing current, which is impossible. I mean, it's not impossible that the current's going this way, but if the current is going that way, that means you have your voltage flipped. And it's not impossible that voltage is correct, but if that voltage is in the right polarity, then the current is going to be flipped. So if you don't use the passive sign convention, there's always going to be a mismatch between your current reference and your voltage reference. But if you use the passive sign convention doesn't say that the current is going in that direction, but if the current is not going in that direction, both the current will be going in the opposite direction and the voltage will be flipped as well. So those both get flipped together. You see what I'm saying? Okay. And this is just saying the same thing but with currents. If you use the passive sign convention, you can use Ohm's Law, I is equal to V over R. If you do not use the passive sign convention, you're going to have to use I is equal to minus V over R. So just use the passive sign convention. That's the conclusion. Another thing that we talk about sometimes is we talk about conductance. some people are kind of upset with George Simon Ohm because he defined the current through a wire as being proportional to the voltage and inversely proportional to the resistance. And some people say, why can't you just define current to be proportional to voltage and proportional to its conductance, or its ability to want to conduct electricity? So we can say that George Simon Ohm was a pessimist. He looked at things and the glass was half empty instead of the glass is half full. He wasn't looking at it, it's promoting current flow, but he's saying, it's a resisting current flow. So he was looking at it from a negative standpoint, and so now everything is looked at in that manner. But you can just as simply...
From a practical standpoint, you can add resistance to a circuit that's not going to add conductance.
Well, you can actually define conductance as being 1 over the resistance, and everything works out the same. And sometimes you'll see G in a circuit, and that means conductance. And that's in Siemens, because Werner von Siemens, the same guy that that started the company Siemens,
Right.
I guess he was a...
Positive person.
He was optimist. Yeah, he was an optimist. And maybe that's why he did really well, and George Simon Ohm, just...
Good.
That's all that's his claim to fame. Okay.
So Ohms died poor.
Yeah. Ohms was a teacher. He was a high school
He
teacher.
died poor.
He was a high school teacher. Yeah, so he died poor.
See,
He tinkered around in the lab, and he just came up with Ohm's Law. I think that's the last slide. So we had one slide to go, and we're done. But your assignment is to read section 4.1 to 4.3. 4.1 to 4.3, and to work out all of the examples in the text and put it in your lab notebook for grading on Monday. And also is to work that test review sheet that I gave you so that we can go over it.
What did you say? What did you say you wanted those? Mr. Halstead?
One of what?
The examples that we work out. Where do you want those at?
In your lab notebook.
In our lab.